Thanks to the organizers for this very, very interesting meeting and for also giving me the opportunity to speak here. I would like to talk about defects in three-dimensional topological field theory. The talk will basically have two parts. In one, I want to explain how to describe line and surface operators in Rishtik and Turayev TFTs, and I will give two applications. And then I want to say, how can you gauge these surface and line operators to produce new TFTs out of the given TFT? And all of this will happen within Rishtik, a semi-simple Rishtik and Turayev theory, so sort of a traditional setting, but maybe the presence of surface operators then makes it interesting. Good. We luckily already just heard a talk by Ilka, who already explained how you describe topological field theories with defects as functors out of a stratified Bordism category. So that's also my point of view. So what do I mean by a defect TFT? You just modify the Bordism side, but the rest of the formalism stays the same. So if I just do the unextended version where I have d-1 dimensional manifolds and d-dimensional Bordisms, well, then the TFT is still a symmetric monoidal functor out of this. But now the Bordisms are more complicated. They are stratified, and the various strata or connected component of strata are decorated by some data. Right, so that's, yes.
Is this the same as what Lurie could work in the singularities?
And now, at some point, you have to decide what is your decoration data. And if you extend it down to points, there's a reasonable thing to do is to just decorate your strata by your target, and then you get, I think, pretty much to what you're saying. But these are not necessarily fully extended. So, goody. So one thing you have to do now, it gets sort of more complicated because now you have to decide, well, what precisely do I mean by this? So what's the data I want to decorate this strata by, and what sort of geometric structure do I want to put, right? Even in if you just do defect TFT without defects, then you still have to say my Bordisms are oriented, do they have a spin structure and whatnot. And now you have to do this for every stratum, right? So in principle, every strata could come with its own geometric data. Maybe some strata oriented, maybe some carry a spin structure. And so that's some extra things you have to decide what kind of topological field theory do you want to talk about. I'll mostly stay oriented, and I'll say a few things about spin, and I'll say nothing about frame. When you talk about defect TFTs, there are not so many explicitly computable examples. So after having been at this conference for this many days, there are more examples than I thought, but that's not so many. And what we will do here is I will look at the sort of one standard type of TFT in 3 dimensions, which is Rishtik and Turayev type TFTs, and I want to equip this with to make this work on stratified and decorated form. That's the plan. So let's have a crash course in Rishtik and Turayev TFT. So our input data is a modular fusion category. So I'm semi-simple here. And what the Rishtik and Turayev construction gives you for that is a functor out of a 3-2 Bordism category with some slight complication, which I will ignore, but which has embedded ribbon graphs, which are colored in this category C, right? So you have your Bordism, and in it, you can have some framed ribbon graph, maybe coupons, and so on. And to all of this, the TFT assigns some linear map from that state space to that state space. And notice that Rishtik and Turayev theory is already a defect theory. You already have a stratified manifold. You have 3 strata and 1 strata, but no 2 strata. And already the kind of geometric structure you put on each stratum is different. So on the top dimensional one, the 3 one, you just have an orientation, but the 1 strata are framed. So already sort of this different strata treated differently appears in this very basic setting.
Sorry, when you say that Rishtik and Turayev, you only have an orientation in the 3 in the pole, that ignores the framing anomaly, or?
That's my hat, which I am ignoring.
Okay.
So there's the framing anomaly, and I don't want to talk about it. But that's also geometric structure, and that's also. I'm also not telling you what precisely I do at the points. Okay. Step 2, you want to add 2 strata. So I first want to say, what do I label them by? And I label them by separable symmetric Frobenius algebras in the modular fusion category C. Okay, and so what I have to do is I have to give you some algorithm which allows you to evaluate a boardism like this one, where you have some 3-dimensional boardism with embedded 2-dimensional strata, which can maybe meet along 1-dimensional strata and produce a linear map. And the way this works is you take the surface, you triangulate the surface, and you put you decorate the dual triangulation by the corresponding algebra lines. And then, because this is a Frobenius algebra, the way you have precisely triangulated this doesn't matter. You always get the same answer. So this boardism, after evaluating it in Rishtikin-Turaev, will only depend on the surface, but not on precisely what network you've chosen on it. Right? And so also now, how the lines are treated changes slightly. So now if you've got a line defect which lives on a surface, well, that's not just an object in C, but now that becomes a suitable modules over the algebras which describes the adjacent surface. Okay, so that does that make sense?
So when you write ZRTC, you mean I can glue these as well along?
Right. So now on my surfaces, I can the surface defects will end on lines on the 2-dimensional gluing surfaces, and I can glue these. Yeah, so it's a functor step. That's what I say on the next slide. Yes.
Is it obvious that every topological shipment could break up into?
Comment this, and the answer is no. So I will comment on this in a bit. So firstly, you do get a functor, and it has all these strata in it, and so the 3 strata are oriented and unlabeled in what I've just described. The 2 strata are oriented and labeled by a separable symmetric Frobenius algebra in C. The 1 strata are framed and labeled by suitable modules over at the algebras of the adjacent surfaces, and the 0 strata are also framed and labeled by appropriate module morphisms. Now, what these numbers mean is that I want to make a comment on all of these points, and the comment you asked about will be comment number 1, but it'll only come after the example. So here are some examples, which we have already seen some of in Noah Snyder's talk. So in SU2 Chern-Simon theory at level K, you can ask, what surface defects do I get by that method? And you get this ADE classification. So how many surface defects, simple surface defects you have in the theory depends on the level, and depends on odd, even, or whether it has these 3 special values. And you either have only 1 surface defect, which will be the transparent one, so the trivial, the identity one, or you can have 2, or you can have 3. And you have then complete control, and you can compute whatever you want. For example, you could compute how do these compose under fusion, and I've just written out some fusion rules to say, to make the point that that's possible. And one thing you can see from the fusion rules is that there's very little invertible happening here. So really the only invertible things are the identity and the D-type defect. In the case, the label is 2 mod 4, and all the rest is not inverted. So you got quite a few, yes.
Is the topology value that you choose in algebra, or are you choosing one?
So it's like these are independent choices. So you have a stratification, and for each stratum separately, you can decide what label do you attach to it. So which algebra do you attach to it? So yeah. So the answer to that question is no. Right, so I will make a comment about this. That will be, I think, comment number 3. So back to the things I want to make comments about. So the first one was this one. So I said the 2 strata are labeled by separable symmetric Frobenius algebras. So that a priori is a very special situation, because what I'm doing is I'm saying I'm only looking at surface defects which are obtained by gauging line defects on the surface. So right? That's what this network of lines was. It means I'm gauging a line which can live on the trivial defect, and I'm gauging that to get some non-trivial defect. So these are not all surface defects. They are not. For example, you can always do a stupid thing and tensor it with a non-semi-simple 2D TFT, and that's again a surface defect, and it's not of that form. Or you could do more complicated things, like maybe one can take the 2D series which Ilka described and sort of couple them to this. So there's definitely much more than this, but I don't know if that's the case, but one could maybe expect that the surface defects whose algebra of point operators on the surface defects, that's finite dimensional and semi-simple. I think these may be all of them.
Sorry.
Yeah.
Question. So when you tensor with any other TFT on the 2D defect, it's not going to interact with any other line and any other defect in the series. So is there a notion for which maybe if you mod out by this kind of tensoring, the defect you're describing are all possible defect or all possible surface defect in your theory?
Right. So just as words, I think that may make sense. I wouldn't say how to say this. I wouldn't know how to say this mathematically. But it's a little bit like what I'm saying here. If I don't have these situations, but so if I do this, what happens to my algebra of point operators? It becomes still commutative, but not semi-simple, for example. So this requirement kills this, for example. Okay. Good. Next comment. So what about two strata being oriented? Well, that you can also get rid of. So we said the two strata are oriented, decorated by separable symmetric Frobenius algebras. But if you drop the symmetric condition and replace it by the Nakayama automorphism of the Frobenius algebra should square to 1 rather than, so if that is 1, then the algebra is symmetric. If it squares to 1, well, it's not. And then in order to make this gauging procedure well-defined, you need to put a spin structure on your two stratum. So that would describe two strata with spin structure. And if you want examples of this, typically you may, so if your C is unitary, if you want examples of this which are interesting, you have to extend the formalism slightly to make your ribbons be labeled in C box S vector, and it has to length in S vector. Okay, so you can drop this requirement to two strata oriented. You can also make them spin if you want to. That's possible within the formalism. Then what Jenny just commented on, I wanted to say, so the three strata were currently unlabeled, but you can extend that formalism to also label the three strata, and then you would label them by modular fusion categories. And by modular fusion categories, but they have to live within a given bit class, or they can't talk to each other across domain walls. So so you have the same formalism where you now label the three strata. It becomes more complicated, but there's still a formalism for it. Now that has some relation to what Jenny talked about, but what Jenny talked about was much more general in that firstly it was categorified. So here to a three manifold I'd assign a number, whereas he would have gotten the vector space. And for me, these are semi-simple, and for you, they were more general. So good, I have to understand that better. And I wanted to.
Are your M's only equivalent to invertible? Did you say that? You only allow invertible defects?
No, why do you say that?
Well, why do you say that the C and D would have to be in the same weight class to have a map between them? Like if you have a non-invertible map.
So I'm claiming if you can write down anything non-zero here, then they're in the same bit class. In the semi-simple setting. That's right. Okay. The safer statement is the only way I know how to write down something non-trivial is if they're in the same bit class. But it's like also, so do the folding thing. So you fold this over and you ask, when does the resulting theory have a boundary condition? Well, that happens if it's a Drinfeld center of something. But for that to happen, the two needed to have been in the same bit class to start with.
That's an invert. Okay, we can. I'll ask you
If
later.
they're not in the same width class, then the domain wall cannot be topological.
Right, that's another way of. So, of course, you can have non-topological domain walls between anything you want.
So another instance of this was when one of the theory is trivial, then I think in Theo's talk there was an instance where you can not have an invertible defect into the vacuum, so to say. That's only when the Hopf algebra happens.
Oh, okay. That's why I asked if M had to be invertible. If you're allowing M to be non-invertible, you could have any braided tensor category you want, and
Maybe in your so okay, maybe in the categorified setting. Not totally sure if that works in this three-dimensional gets a number setting, but yeah, we should talk about it.
There's an off by one thing here because it's a 3D TQFT, but you're thinking about a 4 category, David. And so that off by one comes out exactly here. But anyway, maybe hopefully that.
okay.
I think here you're requiring that you're neither on the anomaly. That's really telling you in the same class.
Okay. Right, now I wanted to give some applications, 2 applications. One is in this symmetry TFT framework. So that's the idea that if you have an n-dimensional quantum field theory, well, you can model it by taking an n+1 dimensional topological field theory with one non-topological boundary condition and one topological boundary condition, so that as you think of this as moving very close to the non-topological boundary, it becomes an n-dimensional fully local quantum field theory. And an instance of this which is realized by this Richtigen-Turaev theory is the following, where the you work in n is 2, so that's 2-dimensional as in the picture, and what you assign to the non-topological boundary is the space of holomorphic and anti-holomorphic conformal blocks for some vertex operator algebra, which would now be a tensor product of something holomorphic and something anti-holomorphic. And in this talk, I will take these to be the same. So the holomorphic and the anti-holomorphic UA, they are the same. And we will see in a moment why I want this. But if they are the same, then the 3D topological field theory, which they sit at the boundary of, is the Richtigen-Turaev theory for this product, C box C bar, which is the same as the Drinfeld center of C. And the category C in question here is the category of suitable representations of the VOA, which has to be rational to make this work. And okay, so in this picture, well, and then the boundary conditions in this pictures are C module categories with trace. And so in this picture, how do you get some of the data of the quantum field theory? Well, there will be some excitations of the quantum field theory which already live on the non-topological surface, and there are others, point-like excitations, for example, which you can obtain by drawing a Wilson line which starts here and is non-topological here, but it has a topological junction with the topological boundary at the bottom, and that would describe a sort of a non-trivial field in the quantum field theory. So now I want to present the same picture slightly differently. So what I want is to unfold that picture. So I start here. That's a picture from the previous slide.
It's holomorphic means the same thing as chiral.
Yeah.
I thought that this is the thing. Something I thought the topological field theory that you got only depended on the chiral thing, on chiral aspects of the CFT.
So okay, so then maybe I say better no to your first question. So what does chiral mean, right? So originally it means sort of and it has a chirality, but it doesn't say which one. But now there's like chiral and anti-chiral, and so you put connect holomorphic and anti-holomorphic and a chiral if you want. But so what I'm saying here is that in this picture where you have a boundary which is topological and a boundary which is not topological, you have to use you have to extract from your quantum field theory the fields which are on the one hand holomorphically dependent on their insertion points and those which depend anti-holomorphically on the insertion point. You need both of them. And sort of that goes away in the next picture where you sort of fold this up, and then sort of both of these sides have holomorphic dependence, but you've sort of flipped the complex structure. Okay, so that was the picture from last time. I want to unfold it, and then my TFT is now only C, and my boundary condition becomes a surface defect. So I'm happy because I've got surface defects again. But it looks different than the symmetry TFT picture one is used to. But there is a point in doing this, which I am not sure, it may only be applicable to two-dimensional conformal field series. But if you have this point of view, what you get for free is that you can now also talk about physical boundary conditions of the two-dimensional QFT, which you want to describe. So non-topological conformal boundary conditions can be described if you work in that picture, because what you do is you take the non-topological boundary and you just bend it around. So that sort of inside here, you still have this holomorphic and anti-holomorphic dependence, but you now also have this sort of seam where it flipped over, where you could insert boundary fields. And now in this formalism, then the surface defects described how the holomorphic and anti-holomorphic side talk to each other, and line defects which can bound the surface would describe different boundary conditions, different non-topological one-dimensional conformal boundary conditions to your field theory. And the reason why this works is a very old observation by Cardi from the 80s, which is the following. So for those who like conformal field theory, so consider a two-dimensional conformal field theory in the upper half plane with some conformal boundary condition along the real line. Then among the fields of the theory will be the holomorphic and anti-holomorphic component of the stress tensor. And the fact that that is a conformal boundary condition by definition means that as you take T to the holomorphic boundary, that is non-singular, and on the boundary it becomes equal to the expectation values of T bar. So on the boundary you have the equation that T of x is equal to T bar of x, right? But T bar depends anti-holomorphically on its insertion point, and T depends holomorphically. So therefore you can have a correlation function of T bar up here expressed as an analytic continuation of a correlation function of T, right? And so that's being modeled by this process. And I don't know if this works in higher dimensions, but in 2 dimensions it's nice because you can use purely topological things to describe two facts at the same time. One is how you couple the holomorphic and anti-holomorphic degrees of freedom, and the other is what conformal boundary conditions the resulting theory has. Okay. So there's a theorem which says that this procedure of putting a surface defect between the two slabs gives you all 2-dimensional conformal field series whose space of fields contains V tensor V, so they are the same VOA, and that is rational, and then there's some small print, and then you get all CFTs by that construction. So that's nice. So it's sort of complete. The surface defects completely parameterize the 2-dimensional conformal field series you can build when you say that the non-topological boundary is conformal blocks for my VOA. That was one application.
There you go. And if you insert different topological surfaces in there, that corresponds to CFTs that are related by like orbifolds.
Yes. So it is also correct that if you put different surfaces, so in this, so if the surfaces allow for an interface, then one theory is related to the other by orbifolding. That's if there's a one-dimensional interface between the surfaces, but that's automatic in this setting. So yes.
Sorry, is there a constraint that the left and the right sector are put together in a modular invariant way, or not necessarily?
So that's my next application, but that surface defect does that automatically for you. So if you think of this, which looks like a torus, as an actual torus, then if you say do some Dehn twist along this side, well, how would it change the surface defect? Not at all. So the picture would look the same afterwards, and so therefore you automatically get something which is modular invariant.
Can you have 2 different surfaces, which makes the same modular invariant?
And different, what does that mean?
That you put 2 different surfaces in the middle, but you get the same surface at the end.
Like 2 different surfaces here? Or
Yeah.
you could put 2 parallel surface defects, but then that's the same as putting just one and fusing them and decomposing it, and then maybe the theory is not simple. It's not what you mean. Okay.
pick another color, like, you know, purple, but orange, pick another one.
Yeah.
That's when you get this.
So you have a bunch of
Oh.
surfaces, you choose.
So can a different surface give me the same CFT?
Yeah.
So I said these surfaces are labeled by Frobenius algebras, but really they're labeled by Morita classes of Frobenius algebras. And if you do this, then no. So then different surfaces will give different. Okay, second application is to mapping class group representations. So that's a math application if you want. So let's look at this picture here. So that's supposed to be some surface times an interval where in the middle I've put a surface defect, right? And you know that if you have a three-dimensional TFT, then on its state spaces it assigns the surface, you get representations of the mapping class group for that surface, or in this case, the projective representations. And now this Bordism will evaluate to a linear map, like a linear endomorphism of the state space, and that will automatically be an intertwiner for the mapping class group representations. And that's because what does the mapping class do? It sort of glues this surface with a diffeomorphism to that end, and acting with the mapping class group afterwards would glue with the diffeomorphism up here. But these two Bordisms are diffeomorphic because the diffeomorphism acts sort of level-wise and will not do anything to the surface defect. So these commute with the mapping class group action and they give intertwines. And that observation was used by these authors to make reducibility statements about mapping class group representations, which come out of TFTs. And it has I should have said that earlier. So the people who are here, I've marked in yellow in case you want to discuss with them more. Sorry?
IR is not in yellow.
That to the audience, to the team. Okay, and so this statement has a sort of funny or surprising converse, which is that if all mapping class group representations for all surfaces are irreducible, then the TFT doesn't have any non-trivial surface defects. So the math statement is that then C is its unique simple module category. So that's surprising. So it's somehow it gives a link between these mapping class group representations and this higher representation theory for the tensor categories. So I don't know what to do with that statement. I just find it a pretty statement. Okay. So these are my two applications. Now I would go to the second part where I talk about orbifolds. Are there any more comments or questions?
Where did the reducibility happen?
Sorry?
Where did the reducibility happen?
Where it happens.
Yeah, I don't quite understand. Your picture implies that if you're all irreducible, then you have to have no surface defects.
Yes.
Yeah.
So, right. Okay, that sounded like the correct statement. So
Yes, I'm confused about where that equal from your picture.
I want you to sketch the proof of your theorem.
Or
okay, I see. Jordanes. So let's see.
I didn't know if it was implied by the. It was supposed to be implied by the picture.
No. So with this picture, I want to explain why surface defects have anything to do with mapping class representations. So it tells you that. So what they actually show is that when you have non-trivial surface defects in West-Witten models, then the mapping class group representations for genus larger than one are always reducible. So that's what they show. And then that's sort of a kind of converse where you say if they're actually all irreducible, then there conversely are no surface defects. And because there's an extra condition for them, which I didn't mention, which is why that's not a trivial converse. Yeah.
The surface defect, there are two possibilities. Either it's invertible or it's not invertible.
Right.
So how do you detect this? By looking at the modular invariance that it constructs?
That's a previous application, right? Okay. Let's go back one. So that would describe a modular invariant, right? And so now I can ask, can I read off properties of the surface defect from looking at the modular invariant? And now what you can also do is write the modular invariant as this matrix that ij, where I and j label the irreducibles. And if the defect is invertible, then that matrix also invertible. And if defect not invertible, then that matrix is not invertible. And so you can read it off from in these examples, right? You can read it off from the matrix.
If the defect is invertible, basically you are gluing left and right with an automorphism of the vector.
Okay. Then we do come to part 2, where I want to do orbifolds. So there are 3 sort of names which I use synonymous. It's generalized orbifold and gauging possibly non-invertible symmetries and internal state sum models. I think maybe sort of from the procedure, the last one is the most descriptive one. And the second one is the one which is currently most used. So what's the idea? You can do this for quantum field theory or for topological field theory, it doesn't really matter. So let's do quantum field theory at this stage. So you have some d-dimensional quantum field theory and you have some control over its defects in various, in all co-dimensions. And then you would fill your quantum field theory with some foam and label each stratum by some predetermined datum for that dimensional stratum. And then you want to impose on your data, which you label the strata by, that the outcome shouldn't depend on how precisely you've put the foam in your model, right? So that's basically a state sum construction, if you think about it. And now I want to implement that in 3 dimensions and then specialize to the algebraic data of this Richteken Torayev type theories. So, so one can take different paths depending on what kind of output theory you want. So I want to get an oriented theory back when I start from an oriented theory. So that's what I will do, but other formalisms are available. Okay, so I want to do an oriented theory, and then I have what I have to do. If I want to do this in d dimensions, I have to fix a set of labels for the strata of dimension d-1, d-2, and so on. And it turns out for the 0-dimensional one, you need to pick 2 because of some orientation choices you need to make. And then you check that this data is invariant under Pachner moves and under the choices of orientations you have to make. And technically, we work with dual stratification. Okay. So what does this look like in 3 dimensions? So that's a possible stratification then of a 3 torus. And you want to impose now, so we have 2-dimensional defects, 1-dimensional defects, and point defect labels. And of these, we have 2, this alpha and then alpha bar down here. And we have to impose invariance conditions to make sure it doesn't quite matter what sort of foam we put into our 3 torus and to be sure that it always evaluates to the same answer. And there are 3 moves and their inverses which guarantee this for you. One is a bubble move, which allows you to insert a little bubble. One is this loon move or L move, which allows you to move a line across another line. And then there's this T move, which allows you to, again, move a line across such a vertex here. And so if you can guarantee that your construction is invariant under these 3 moves and their inverses, then it will be invariant under which foam you put, provided it's fine enough so that all cells are contractible. Okay, so let's do this algebraically. So in this Richteken Torayev example, which I described, I said surface defects are described by algebras and lines by certain modules and so on. So I can now translate the data I need into some algebraic data, which happens in my fusion category C. We call this data orbifold data, and it consists of 2 objects, A and T, in the category C, and then some morphisms. And so the first thing we need to choose is a label for a surface defect, which means we have to point at a symmetric separable Frobenius algebra, which typically will not be simple. We will see this in examples. Then we have to point at a junction line, which allows to join 2 such surfaces to 1. And algebraically, this means we have to point at an A tensor A bimodule. Okay, and then we have to find a way to cross these junction lines over each other. So we have to choose a point defect, and that'll be a morphism from T tensor T to T tensor T in the category C, but it has to be compatible with the actions in a way which I'm not explaining. And then there's some extra data, which I'm also skipping over. Right. So that's the data. And then there are conditions. Here's one condition. That's the move where you move the surface over a crossing. So it has sort of 2 crossings here and 3 crossings here. And algebraically, it translates into this string diagram. So that's now an identity of 2 morphisms between t to the tensor 3 in the fusion category C. That's the geometric condition I want, and it becomes an algebraic condition over here. And then there's a whole host of more conditions, which I've listed here. I'm not going to go through them. The top one just means that this junction is invertible in a suitable sense, and the ones which I've labeled, or that these are necessary to get rid of orientation choices you had made along the way.
Can I ask a quick question?
Once you've picked the data and satisfied all the conditions, you can build out of your given TFT a new TFT. So it's now an algebraic problem. I want to give 3 ways of also thinking about this algebraic data. So I gave it sort of very explicitly algebra, bimodule, and some morphisms, but there are more basis-independent ways of looking at this if you want. One elegant one is to think of a monoidal category which is enriched in the ribbon category which we use to define the TFT. Right, so that's one way to think. Well, I should say of the data without the extra conditions dealing with orientations. So that's one way to think of it. Then equivalently, you can think of it as something called a module monoidal category over the braided category defining the TFT. And what's the module monoidal category? Well, you can think of it as a functor. So you should think of this as a categorification of an algebra over some commutative ring. So you can either write this as a braided map from C into the center of M, or where this name comes from as a monoidal category with a compatible action by C. Right? And I claim that that data also corresponds to this explicit algebra, bimodule, and so on, provided I forget these extra conditions. So why am I saying this? I'm saying on the one hand, you have this very explicit data you can work with, but there are also more sort of Morita invariant description of the same situation. Huh? Sorry? Yes, that's in the that's the job of this PhD student. So yeah, it would indeed be good to know what that would be the existence of some adjoints and so on in this language, but the details to be seen.
Sorry, maybe I'm imprecise, but if you receive to a special case that A is just the identity, is trivial.
This one or that one?
The one inside the parentheses.
Yes.
Then do you get back the old condition that T has to be a Frobenius algebra?
No, but I will give examples and then we will see what that looks like. So T is never, so there's no condition for T to be net. So the condition for T is this one, right? So there's nothing which looks like an associativity for T.
Yeah, that is why I'm confused, because I'm comparing with the old your old works where I mean when it was the gauging just of the lines.
Yeah.
And the line was
right, but I will have that example. So we will get to this. So this, yeah. In this setting, it's described slightly differently. You would actually use, if you want to just gauge a line, you would also use the same line to create a surface and then gauge that. That gives the answer you expect. Right? Okay. So I described the data to so there's sorry. Never mind. So now, I've described the data. I need to use a new TFT. Namely this orbifold data, and now I am asking what do, for example, line defects look like in that new orbifolded theory. And from this picture, that what the orbifold does for you is it just fills the volume with some foam and evaluates in the old theory in such a way that it's independent of the foam. Well, if you want to define line defects in the orbifolded theory, then you should look at line defects which somehow live on the foam in the old theory. So that's the idea. So we want to want to somehow describe what it means to draw line defects on the foam in a way that is invariant. So that's happening here. So drawing lines on the foam, well, that's a line defect which lives on a surface defect, and algebraically it becomes a bimodule over the algebra, which describes the surface. Then it has to be done invariantly. So in particular, we have to be able to cross over these junctions in different ways. Well, that means part of the data of this line should be preferred ways to cross. And so that's morphisms from this tensor product into that tensor product. So that looks a little bit like a half braiding, but there are two of them. So and then there are lots of conditions that you can move the line around in the foam in an invariant way, and these translate into algebraic conditions, which you can write out, and I didn't write them all out. But if you do this, you obtain a category of line defects. So you just do this problem in representation theory, and you get some new category CA. So that's a category of line defects which live in the orbifold. That's also a ribbon category you can show. And in fact, what you can show is that if you start with a modular fusion category and you have an orbifold datum, it has to be simple, which I didn't explain what that means. Then this category of line defect I described is again a modular fusion category. So you start modular fusion, you do this procedure, get a new modular fusion category. And now you have a modular fusion category. Well, you can plug it into the Richteken-Turaev construction. So you can ask, what is the Richteken-Turaev theory for that modular fusion category? And it's precisely the orbifold of the old one. So this orbifolding procedure doesn't move you out of the class of Richteken-Turaev theories in that example. So these are equivalent functors between these categories. And to get maybe a more abstract feeling for what this category is, look at this line. So this new category of line defects, if you box it with the opposite, also with the reversed category for the modular fusion category you started with, then you get a Drinfeld center of something. So the way to think of it is some sort of relative center. And what this also tells you is that the new category lives in the same width class as the old category.
Can I ask a quick question?
Okay. Yes.
Up here in Zoom. Yes. You're using this, you're using T, you're only gauging T in your foams, am I right? You're decorating your lines with a single guide T.
But I've also surfaces which live between the lines, right? So the surfaces are, so there's T and the surface A, and crossing a junction.
Right, but there's a single object T, correct? You don't have multiple decorations for the line.
There's a single object T, but it doesn't have to be simple, right? So it could be like a sum.
Understood. Understood. But now question is the gauged object graded by automorphisms of T?
Okay, I haven't thought about this, but I'd say something anyway, so you can prove me wrong. So I'd say typically not. I'd say typically it would depend on all the data which you have available. So you need the algebra and the T and I haven't thought about it. You can look at examples. So I will have a number of examples and you can test this in the example.
Thank you.
Okay. And the second point, which is important, is that if you have any two modular categories which are width equivalent, then you can always find orbifold data in one such that the orbifold is the other. So it's sort of a transitive operation. Okay, so here are examples. So in the first example, my surrounding modular category is vect, so the TFT is trivial. And then I fix my orbifold data in terms of a spherical fusion category. So what does that mean? So A is now an algebra in vect, and it's concretely going to be as many copies of the complex numbers as F has simple objects. So the representation theory of A just rebuilds F as an abelian category, and then T will encode the tensor product of F, and the alpha will encode the associator. And so if you do this orbifold datum in vect and you compute what is CA, then you do get the Drinfeld center of F. So the orbifold in this case would give you, it actually gives you precisely the Turaev-Biot construction. Here's another example. If you start again in vect and you pick a finite dimensional semi-simple Hopf algebra, Then you can take the algebra to be the Hopf algebra, just the algebra part. You can build T out of the Hopf algebra, and then there are some expressions for alpha and so on. And if you use this as an input, well, then you get the center of H mod. So that's pretty. So you can also put directly something you like a Hopf algebra, and you get an answer. Now, something which relates to your point. So if I take any TFT to start with, so any modular category C, and I have a simple commutative symmetric separable Frobenius algebra, then I can build an orbifold datum where the algebra is this, and that's what you said. The bimodule is then also built from A, and if I use this data to gauge, I get local A modules as an output. So that's like the condensation of an onion. That's what this builds. Okay, more examples. So suppose I've got a crossed ribbon category. Then I can take its neutral component. That's going to be my modular fusion category. I use this to define my TFT. And then I use the G crossed category to define an orbifold datum. And the algebra looks like this. I don't want to describe it in detail. But you can, out of that data, you can build such an orbifold datum. And if you do compute the category of line defects, then you precisely compute the equivalentization of D, right? So that in a way justifies the name orbifold, because that's an actual orbifold by the finite group G. And the others are maybe some sort of generalized orbifolds. Okay, one more example, sort of more exotic. So you start with an Ising type category, which has three simples, 1 sigma epsilon. And as an algebra, you just take 2 copies of the unit. And as T, you take some strange thing, and then there's some complicated way to do the rest of the data. And it solves all the conditions to be an orbifold datum. And if you compute what's the category of line defects, then you get SU2 level 10. So that's pretty. And what that does is it inverts the anion condensation. So as I said, you can always walk between any 2 modular fusion categories in the same width class. And so in particular, it has to be possible to invert anion condensation. And that's an example. So if you want to go back, so you can go from SU2 level 10 to an Ising type category by condensing 0 and 6. But you can also go back from Ising to SU2 10. Yes, with that.
Ingo, you forgot some yellow, no?
Yes, why? Yeah, I unfortunately forgot to say yellow when the first yellow name appeared, which was Vincenzo's name. Yeah, sorry, also yellow. Good. Now, remember that I wanted to make one more comment. So it's okay. These were my examples. Now I want to, so I had these 4 comments I wanted to make about stratified TFT. And there was one which was left, which is, do the 3 strata have to be oriented? And again, you can relax this. In fact, what you can do is you can start from an oriented 3D TFT, and you can do this gauging construction in a way that it ends you up in a spin theory. And so we are working on one example of this, where you take this anion condensation example, but you drop the requirement that the algebra is symmetric, still commutative, but you no longer require it to be symmetric. That means that the twist doesn't have to be the identity, but it implies automatically that it squares to the identity. And then if you do this, well, then you get something which starts in spin bordisms and lands in vector spaces or in super vector spaces, depending on your setting. So you can also describe spin theories in this way. And for example, there's something called a spin modular category, which is just a usual modular category together with a choice of fermion, which means an object in C, which is invertible and which has twist -1. And out of that datum, you can then produce something which lives on spin bordisms and lands either in super vector spaces or in vector spaces, depending on whether the dimension of this object is 1 or -1. And that also relates to the talk we had by Matthew, because you can then make the spin modular category pointed, which means all objects are invertible. And then that describes abelian spin Chern-Simons series. And so one can now use this formalism maybe to investigate what surfaces and surface defects and symmetries it has. Okay, so you can do spin. That was a comment I wanted to make. And I want to come to an application. I'm running out of time. I'm out of time. So I wanted to give an application of this orbifolding procedure to Levin-Wen models, which links to a talk by David Pennies, who has already introduced for us what Levin-Wen models are. So here I can be quick. So Levin-Wen model, you had a two-dimensional spin model where the state space is given by some local degrees of freedom to the number of sites, to the number of vertices here. Then there's some Hamiltonian, which is a commuting projector Hamiltonian built out of vertex, edge, and plaquette Hamiltonians. And one way to get such a Hamiltonian is to start from a spherical fusion category, and then there are some specific expressions which David explained. And if you use these, then the ground states of this Hamiltonian on this model produce for you the state space of the Torayev-Virus theory for the fusion category you put in. So, so Levin-Wen models give access to certain topological phases, and these are the topological phases which are described by Drinfeld synthesis. And I want to use the orbifold construction to give a sort of an internal version of that. So, so what do we do now? We take a modular fusion category, so that defines for us a 3D TFT, and I point at any one anion in that X, and then rather than sort of as we did before, think X a vector space and we just tensor them together for each site, I now take a surface and I put lots of these X anions on it, and I evaluate the TFT on that surface and declare that to be my Hilbert space, right? And so if C is vect, then that reproduces what we did previously. Then we would just tensor together vector spaces here. But now that's not local, so this is not something you can write as some vector space to the tensor insertions. So, but still, I can do this. So it's like putting anions in some already pre-existing topological phase, if you want. And I now want to connect this to this orbifold data I had. And what I need to do is to think of this X as this datum T, so this object T I had. Okay, and then out of this data, this orbifold datum, I can build a Hamiltonian, which has again a vertex, an edge, and a plaquette Hamiltonian. And I only describe the plaquette Hamiltonian. And the plaquette Hamiltonian is given by evaluating the 3D TFT on that surface times an interval. And over the plaquette you want to define this piece of the Hamiltonian on, you put this defect network, where in particular you have this vertical slice where you have the surface defect labeled by A on top of the plaquette. And that defines for you a linear map from that space to itself, right? So you get just, that's a Bordism, but if I apply the TFT, it's just going to be a linear map of that space. I add them all up, and then I've got some Hamiltonian which acts on this. And if I compute the ground states, what I find is that they are equivalent to the ground states of the Rishkin-Torayev theory for this new category of line defects, or the CA category for the same surface. So, so remember that this procedure passing from C to CA allowed us to walk between any two modular categories in the same width class. So from that point of view, what that's saying is that if I have two topological phases in the same width class, then I can realize one as a sort of an internal Levin-Wen model where I put anions in some Hamiltonian, and then I obtain any other width class, any other modular category in the width class I may want. And so I could run this procedure now for all the examples of orbifold data I had given earlier. For example, in this one, where we had the Ising category and this anion X is now that funny combination, and then the Hamiltonian is some explicit linear map. And the ground state space will be described by the topological phase for SU2 level 10. So it allows you to go from Ising, which incidentally doesn't have universal computation, to SU2 10, which does. So that's nice. Okay, I think that's pretty much